Yes, Bismillahirrahmanirrahim. Welcome to lecture number 20. In lecture number 19, we have learned the natural convection flow and the types of the convection. We have a forced convection and free convection. But now, what about the application of the free and forced convection? We also learned some techniques and application of free convection, like in fridge and freezer, the cooling compartment and the top of the sides to have a uniform temperature by the natural convection flow. And also, as well as the forced convection example, we have a cooling fan in the laptops that cool down over the internal circuit of the PC or laptop. Also, there will be now the fridges are coming with the forced convection flow. The cooling plate, when you open the fridge, you won't find any cooling plate, and the cooling plate is hidden behind the block, and the whole fridge is cooled down by the forced convection. There's a fan installed in it, and the fan pushes that cold air throughout the compartment, and both have a different pros and cons. In the natural convection flow, we have a less energy related with the, because there will be no fan, so the flow of the air is totally free and it is natural flow. But in the forced convection, the fan is installed in the fridge, which forces air from the top to bottom and make a uniform temperature throughout the fridge. But by additional energy of a fan, by putting additional energy, by running the fan by additional electrical energy. But both have some advantages and disadvantages. The disadvantages in natural convection cooling plate in fridge is we found the uh, cold layer in the cooling plane. We have a layer of icing. We have a ice layer in the cooling plate which resists the heat transfer, because ice has a low heat transfer as compared to metal. So the liquid metal contacting with the air transfer more heat, absorb more heat, so heat transfer will be higher, so it has a better efficiency. But if the ice layer on the cooling plate comes in the in the cooling plate, so it resists the absorption of heat from in compartment itself. It gives some cooling throughout the surrounding, but the temperature, but the absorbent capacity becomes lower. So now the upcoming fridges are coming with the forced convection, and the fan installed inside the fridge, which you cannot see by your eyes because it is hidden in the compartment. And also you cannot see the cooling plate because it is also in the inside compartment. So there will be forced convection flow. It is about some electric device, but now we have a bigger vision related to the free convection or natural convection, especially related to your infrastructure designs of the buildings. um, let's have some example. Before going to example, I just need to show you the value of H with the different in different forms of liquid gases. And like in free convection, in the free convection of gases, the H value, the convection heat the coefficient of heat convection heat transfer is between 2 to 25. Okay, and the free convection in the liquid is 10 to 1000. So in the liquid we have a higher convection heat convection in convection as compared to the gases. And we are talking about the free convection, that is naturally air or water moves upward due to the density different, and it remove the heat. So the H value is lower in the gases and is higher in the liquid. So basically in liquid are better heat conductor as compared to gases. And what about the forced convection? The forced convection of the gases value can be beyond from 25 to 250. Okay, so now you are pulling some air by some external force like fan, or in liquid case we have a pump. So definitely when we pushes air with the rapid velocity, more air contact with the hotter body, so it will release more heat. So definitely it will release more heat, so the convection heat transfer coefficient will have the higher value of the forced convection. And in the liquid, force convection in the liquid is beyond is value beyond from 50 to 20,000 watt per meter square degree centigrade. And the boiling and the condensation, you already learned that boiling and condensation in refrigeration in CO in refrigeration cycle, as well as in the steam cycle. When we have a phase change from liquid to gas, from liquid to gas, or from gas to liquid, the value of H is even more higher. Okay. Now, what about the application of natural convection heat transfer inside the buildings? This is an example. Now in upcoming nowadays in we have a famous place like in Turkey, where first it is a place for the Christian, uh, for the so it's a Christian prayer area, or it's a church in Byzantine Empire, but Sultan Muhammad Fateh conquered, and now then it's become a masjid, and from the last 500 year, people pray and offer namaz. But in 1930s, Ataturk Kamal convert again into the museum. But now recently, in the last Friday, again the Turkey Prime Minister offered the namaz over there and started it again a masjid. So it is Hagia Sophia, and we have not only this building, but in the previous buildings, you feel that when you goes into that building, you can feeling a cooling effect without any placing of air conditioning, without any fans. You feel the blowing air, and how the blowing of air comes into that kind of sorry that's kind of constructions, because of the circle dome, especially in masjids. We found that domes, the application of domes is because of the natural convection, because we have a large tall area in which, when the person comes inside the mosque or inside the hall, the hotter air goes up, and the colder air from the windows taken place that position, and then naturally there will be a currents of air flows without any placing any external fans and blowers. We have a natural convection flow. So you are most related peoples, because you are going to in a design firm on any other place. So you just whenever you are in designing anything or placing any comfortable zone, designing any comfortable zone, you can include this natural convection phenomena and reduce the external energy taken by the fans and blowers inside the buildings. So these dome structure, by making this dome structure tall dome structure produce a natural currents of flow without any external fans, etc. So we feel a cooling effect, blowing of air from outside air, and the heat is taken away from outside the building without the expense of the fans. Nowadays, I feel that we our building are designed opposite to it. We placed fan on the top of the roof that blows hot air to the ground. Oppositely, we should place fans in the windows, which blow fresh air outside to the inside. And also we have to place exhaust fan on the top of the roofs of building, or we constructed that kind of the building in which we have a windows above on the top area. So we just placed or open that window, so naturally there should be a natural exhaust system. Okay. So it is related to your field, so I just explain it or place some of the examples um, that you can use in your future upcoming professional career. I hope you realize this kind of thing, so uh, buildings become more operational, cheaper, and have a high efficiency and have a better comfort zone for the peoples. Anyway, now we need to come into the numericals. We know that Newton law of cooling formula: Q, the heat transfer rate, is HA Ts minus T infinity. T infinity is the surrounding area temperature, T as the hot body temperature, As is the surface area of the hot body, okay, and H is the heat transfer coefficient. So this is an example 1.8. So we just need to solve it. First we read out and then we solve it. So it is a, basically I just need to uh, clear the surface area now. Yes yes in this particular example, when the heat is blowing towards that area, the surface area will be this, okay. This will be the surface area. Now it is a side view, but when you see in the top view, it has a square shape, okay. So higher the area, higher will be heat transfer rate, higher the convection heat transfer coefficient. As you know, as we learned that in the liquid the H value is very higher, in the gases it is lower, and then the free convection, basically we have a lower velocity, so we have a lower H value. But in forced convection we can have a very high velocity by some external force, so we can have a higher value. And how much the temperature difference, there will be the greater will be the heat transfer. So in example 1.8, a 2-meter long, that is a 2-meter long diameter electrical wire extend across a room at 15 degrees centigrade. As shown in figure 1.37, heat is generated in the wire as a result of resistance heating, and the surface temperature of the wire is measured to be 152 steady operation. So all steady means it is not changing with respect to time. So the heat transfer rate, we just take this value. If it is a problem of unsteady, you cannot apply the same formula, because the temperature is changing of this metal rod with respect to time. Also, the voltage drop electric current through the wire are measured to be 60 voltage and 1.5 current respectively. Disregarding any heat transfer by radiation, determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and inside the room. So the outer surface of the wire is contacting with the surrounding air. Now the heat transfer is taken from two kind of surface area: this circumference area of the wire, and the area of circumference is, if we basically if we zoom this, yes, this circumference area of the wire, and this is a perpendicular area of or radial area of the wire. You can see that the diameter of the wire is very lower, so we can neglect this heat transfer rate. Actually there will be heat transfer rate, but in this particular numerical we can neglect this kind of heat transfer because it is a very lower value. So we have three surface by which the heat transfer can take place: this circumference area, this radial area, two radial area, and one circumference area. To to ease that numerical, to make less complicated, we just neglect these two heat transfer rate from this this radial area, and just we take this circumferential area, because we get the temperature of this circumference temperature, not the radial temperature. If we need to find out this, we also need to have the temperature of this radial surface, okay. Now we can so we read out this numerical, we get the values. Now need to solve the numerical. Yes, let's close my this, and we have data. We have a area is how much the surface area. Oh, yes. The For this particular numerical, the surface area will be circumferential area. We just take circumferential area. The formula of circumference is 2 pi r. We just need to have a value of radius. We get the value of area. Okay. Now we have a value of, we need to find out the h, heat transfer coefficient, and we have a temperature of surface 152, that is Ts, 152 degrees centigrade, and we have a T infinity, surrounding area is 15 degrees centigrade. Okay, now applying that formula, q dot, and the q dot will be heat transfer due to the electrical resistance, and the electrical resistance here, power formula will be voltage into current, and this q is equal to h, this is I, sorry, current, h a delta, not delta t, it is ts minus t infinity. Just need to, yes, it is ts minus, sorry, t infinity. So voltage is 60, I think 60 in 1 to 1.5. Yes, 60. We have a voltage. We have a voltage 60 and 1.5 current. 60, this voltage 60 multiplied by 1.5 is equal to, we need to find out h, and this a, sorry, we have to put this bracket also, the whole h multiplied by with ts minus infinity. So a ts minus t infinity goes into the denominator, and the value of a will be it's 2 pi r is circumference multiplied by length. Okay, we also have to multiply it with the length. If we see the picture, let me explain. Yes, this circular area, this circular is formula of is circumference is 2 pi r, and this circumference is elongated to the whole length, and the length is 2 meter long and the diameter is 0.3 centimeter. So the area will be 2 pi r, this circumference multiplied by whole length. Okay, we miss in the when we applying the formula this. Okay, so now this area will be 2 pi, and the radius is 0.3, so we divide by 0.3 with the centimeter, so we can apply divide by with 100 into 2 meter long. This is whole area, and ts is basically 152 minus 15. Okay, again I just did one mistake thing. 0.3 centimeter diameter, it is a diameter. I just did it directly. We have to, remember that when you are going to solve this numerical in your paper, always write data. Okay, I just not did write complete data, that why I just miss some parameter. So right now we have a, zero point 0.3 centimeter diameter, not a radius, and we apply the formula of radius, so we have to divide it by 2 to get the radius. Okay, this 0.3 is also divided by 2, so we can write this like this. This is basically diameter. Okay, and by using this, by solving this, you will get the value of h is 34 point, let's check in the, yes, 34.9 watt per meter square Kelvin. 34.9 watt per meter square Kelvin, or you can also write degree centigrade because it is a difference of temperature, and now it is better to write degree centigrade over here because we have solved in degree centigrade. Okay, now we find out the value of heat transfer coefficient for this particular example. uh, we have some time, so we can also solve one more numerical, very short numerical. uh, I hope this numerical will be clear for you people. It's a very simple numerical. We just find out the heat transfer coefficient. Now for the second numerical, the hot air at 80 degrees centigrade is blown over 2 meter and 3.4 meter flat surface. Like we have a flat surface. Why it is not writing? Okay, we have a flat surface like this. Okay, so we have a forced convection, so there will be some fan which blowing air from this surface area. So we have an area of 2 multiplied by 3.4. Okay, and we have we can solve the numerical over here. Okay, and we have temperature 30 degrees centigrade, and if the average convection heat transfer coefficient is 55 watt per meter Kelvin, determine the heat transfer from air to plate. Okay, we have to find out the heat transfer, that how much the heat transfer will be taken from this 2 meter long and 3.4 meter long and 2 meter wide flat surface. So we need to find out the q dot. Okay, in kilowatt. So here we can go. We have a formula q dot is equal to HATS minus T infinity. We have a H value minus H value is 55, I think. Yes, 55, 80, 30 and 2. 55, and we have area 2 multiplied by 3.4, and temperature, we have a high temperature, surface temperature 80, and the blowing air temperature is 30. It is in degree centigrade. We can write, even you can convert into the Kelvin, the temperature will be same like 50. Okay, so when you solve this numerical, when you multiply whole 55 multiplied by 2 multiplied by 3.4 multiplied by 50, you get 18,700 watt. 18,700 watt. So convert into the kilowatt, it will be 18.7 18.7 kilowatt. Okay, now this numerical also solved, and we also completed our time. So let's so we'll see in the next lecture, lecture number 21 and 24. In between, best of luck for the papers, for best luck for the midterms and final examination. If you have any question query, you can write an email or comments on the stream section of this lecture when I upload it. Okay, till then, Hafiz, I hope I clear many ideas related to the heat transfer coefficient, heat transfer rate, and also give an example of dome structure buildings, how uh, the naturally heat can be reject from the building, and we have a natural blow of air, and the position of the uh, AC and cooling plate in fridges, and a stove or radiator in the room. Okay, so I in the next class we will cover the last topic of heat transfer, that is radiation. And after radiation 1 to 2 numerical, we will go towards the overall heat transfer, in which all the modes of heat transfer taken place: convection, conduction, radiation, and also we solve the numerical related to the building construction of the buildings, like actual wall of the bricks, and insulating materials with the added with the insulating materials, so you can apply in your after graduation, you can apply on your own field or in your own design criteria. Okay, till then, Hudafis, best of luck for the midterm and exam.